Thank you very much. It's of course a great pleasure to be at this opening meeting of what is likely to be an exciting period. This isn't directly related to the PDEs. It's addressing what I think is quite a fundamental question I've been looking at and been interested in for some time. And for a long time we were making no progress, and suddenly we seem to have made some progress, and that's just what I want to tell you about. So I want to start by setting the scene a bit. I want to start by reminding you of a theorem that surely you're all familiar with, and because in some sense what we're talking about is a generalization of this theorem, or at least analogous to it. I guess everybody knows that if we take the circle T and we look at an L1 function on the circle, we can compute its Fourier coefficients because we've got our L1 function times a bounded continuous function, and these actually determine f in L1. But actually, when you stop and think about it a little bit, the reason they determine f in L1 is the Stone-Weierstrass theorem or something like that, because the finite linear combinations of exponentials are a algebra, and we know that a measure is in the dual of the space of continuous functions, and so we know that because this is a dense set, we've characterized our measure or our function in L1. But actually, unlike in L2, it's actually quite difficult to be sure when you're given a set of coefficients whether or not there really is an L1 function associated with them. And it's actually quite hard in some sense to go back to the L1 function or the measure. In L2, of course, we know that we can construct best L2 approximations and so on. And so there's lots of naturality, but even in L2, of course, the pointwise convergence of Fourier series is a problem. The other point I want to pick out of this picture is actually it doesn't really determine f in L1. It determines the measure, and in particular, if we did change f on a null set, we don't actually change the Fourier coefficients. It's not really a one-to-one map, it's a one-to-one map on equivalence classes. And the equivalence classes need you to have Lebesgue null sets, and of course the invention of Lebesgue measure was a big step forward in understanding Fourier series. Well, I'm not interested so much in the abelian group, which is the circle. I'm interested in a very non-abelian group, which isn't even quite a group, which is the paths of finite length. And I guess all of us understand that if you have a path in a metric space, a path is just a map from an interval into that space. We can talk about its length or its finite variation by taking a partition of time, and we can look at the increments of our path over these time intervals. We can look at the distances between them, and we can add them up. And we can take the supremum over all possible partitions. It's not difficult to define the length of a path in a metric space. But if it's just in a metric space, there's not a lot else you can do with it, except you can split it. If you've got a path in an interval, you can always break it into two shorter paths which join at the point of splitting. It seems a strange thing to do, but it's a meaningful thing to do. And at an algebraic level, it's basically that there's a co-product. But if you're in a vector space, life changes somewhat. If you're in a vector space, if you've got one path and another path, then you can always translate the second path, put it at any end of the first path, and you can concatenate the two. So there's actually a natural algebraic structure and operation in there that allows you to concatenate. You have to be a bit careful of what you do with timescales, but providing you don't do anything with the timescales, it's a nice associative product. Well, I want to explain to you today, first of all, some very basic theorems about these paths of finite length. Then I'm going to explain to you why they're true in some loose sense. And then there's going to be basically a fundamental open question, and I'm going to explain to you in part how one begins to be able to solve it. So the first thing to understand is that if we're interested in paths because what do they do for us, like in probability theory, if we're interested in them because of the way that they drive differential equations, then there's a natural notion of a null path. And this notion of a null path you can write down mathematically, and I have in the second box, but it's often difficult the first time you see it to get a grasp of what that definition actually means. But I think we all have an intuitive understanding of what we mean by tree-like path, and that is the mathematical way to capture it. So a tree-like path for me, and I hope for you, is one where you go out, but every time you go out in a direction, you come back exactly in that direction and undo it a bit, and you go out and you come back, and you go out and you come back, and finally you come back, and you unravel everything you do in the order in which you do it. You can do quite complicated things on the way, but you always come back along that bit before you do something else, and you can come back and so on. Now, the interesting thing about a tree-like path from the point of view of probability or the point of view of control is that it should be obvious to you that if you drive a differential equation by such a path, then you should actually end up, if you're doing Stratonovich or if you're doing classical differential equations, where you started. If you roll a ball along this path, then everything you ever did to this ball, you exactly undo before you do something else. So the nature of a tree-like path is that you actually undo everything you've ever done. And because you do them in the right order, you never get the lack of commutativity coming in and changing everything. If you did a figure of 8, of course, somehow undoes things that it does, but it doesn't do them in the right order, and there's definitely going to be differential equations that see the difference. But a tree-like path is one that instinctively or intuitively is one which, when you drive a differential equation with it, you get back exactly to where you start at the end. It has no effects. As soon as you include time in a path, so you take a path and you add time, it's never tree-like, because the time is evolving in the forward direction. So typically paths are tree-like if they don't have a well, they may be tree-like if they don't have a time component. By the time you put a time component in as part of your path, it's never tree-like, because it's evolving forwards and never undoes itself. So we can grow old. So the important point, I suppose, is that you do need an analytic definition. We have this intuitive definition, but it should be clear to you that we can add little bits to the big bits. And we can add little bits to the little bits. And we can add smaller and smaller bits. So essentially you can have continuum type tree-like bits, where each little bit has little bits inside it, sort of snowflake type pictures. So you need an analytic definition. Unfortunately, it's quite easy to give. So if you imagine a tree, a rooted metric tree, then there's a natural notion of distance between 2 points given in terms of the height. The distance between this point and this point is the distance back to the root plus the distance back to the root minus twice the distance to the nearest point on the path between the two to the root. So if you imagine h as a positive real valued function on an interval, you can imagine it as giving you the height in some tree. And indeed, you can actually really make that precise. And so then you have a natural notion of distance between points in the tree, given, as I said, by the height to the first one. There should be a t in there, I apologize. That second one here should be a t. The height to the first point, the height to the second point, minus twice the smallest value of the height on the path between the 2 points. So that's actually just the distance on a tree, and we're saying that the distance between the points in the path should be less than the distance on the tree. In practice, what it means is that you can find a metric tree and a contraction of that metric tree into your space. So the original path was obtained by exploring the tree and projecting that exploration down into the space. It's a very natural idea, but written in the form in the second box, it's much more powerful because, for example, you can see that limits of trees are trees. You can understand that under certain reasonable conditions, like, for example, they all have bounded length, or the h's have bounded length, then if we take a pointwise limit of trees, it will be a tree, and various things like that. That's a lot of closure properties.
Gamma is in a linear space?
So hang on, yeah? This actually doesn't need the linear space.
Because you have...
This actually has no need for the linear space whatsoever, except that I shouldn't write mod, I should write distance, right? But everything I'm going to be talking about really, because I'm interested in the concatenation, we'll be talking about linear spaces. You can make everything work on manifolds, but it's just a little bit more technical, and so I'm certainly not going to do it today. Well, once you have this understanding of what it means to be tree-like, it allows you to introduce a relation between two paths. So we can say path A and path B are related. So think of this as L1 again. You need to understand when two functions are the same almost surely. Two paths are related if the first one and then the second one run backwards, taken together, is tree-like. So by now, you have to be in the vector space because you don't actually, but you have to concatenate the one with the other. And it's sufficient that it's in a vector space. So the idea is you take a path, and then you take the other path and run it backwards, and the two together should be tree-like. So it's obvious that the path is related to itself, because if we go out along a path and then exactly back along the path, this is obviously tree-like. Okay? It's also obvious, from what I was just saying, if you believe what I said before, that if the composition of this first one and the second one run backwards is tree-like, then if you drive a differential equation by the first, or you drive a differential equation by the second, you'll get the same answer. So this is a natural notion of equivalence, in a sense, in terms of their global effect as driving terms, as controls on a dynamical system. They will produce the same answer. You'd like to say it's an equivalence relation. But it's not at all obvious that it's an equivalence relation. In fact, it's true that if the paths have finite length, it is an equivalence relation, but this is actually a consequence of actually a large number of pages of math. And what's the problem? The problem is that to be tree-like, you need this witness, this height function, h. And the height function you get to get A equivalent to B doesn't necessarily have any relationship with the height function used to get B to be equivalent to C. And so the trouble is you can't obviously see that this relationship is transitive. It seems intuitive that it might be, but it's not obvious at all. The point is that if you have a tree-like path, there is no canonical height function. It's just like in algebra when you look at the free group and words. If you have a word, you can always cancel it down to a reduced word, but there's more than one way to do the cancellation, even though at the end you end up with the same reduced word. There is no uniqueness about how you do the cancellation. And for an algebraist, that doesn't cause trouble because they only have finitely many and they can use induction. For an analyst, it causes a lot of trouble because we have uncountably many and no obvious order in which to choose them or select them. So that is actually the problem. There is nothing canonical about the H that you use to witness the fact that it's tree-like. There can be different ways to do the cancellation. But anyway, it's clearly an interesting relationship. And clearly, if two paths are related in this way, they will have the same effect on a dynamical system. But just as in the free group, you can talk about reduced words. In fact, to get the free group, you do talk about reduced words. You start with all words in an alphabet and its inverses. You do the cancellations and you end up with words that have no cancellations in them. You can introduce the same sort of ideas for paths. You see, you could say that a path has tree-like segments if I could find some interval of time, and so that the path on that interval of time is tree-like. The whole path doesn't have to be tree-like, but we could find an interval where there was a tree-like piece. So from the point of view of driving a differential equation, we could erase that piece. It would have no effect. We can say a path is tree-reduced if it has no such segments. And it would be nice, if it were true, that in each equivalence class, well, we don't yet know even that it's an equivalence class, but if we did know it was an equivalence class, it would be nice to know that there was a representative of that equivalence class that was tree reduced, and it would be nice to know that it was unique. Well, it is an equivalence relation, as I mentioned before, and if you want the proof, I think it's, we were tossing like minor trivial page proof things around this week. I'm pretty sure we have page numbers for the January edition of the Annals of Maths, so probably it's going to appear in the next week on their website. It is an equivalence relation, and it is actually a fact that if you look at the equivalence class associated with a given path of finite length, there is a tree-reduced path in it, and there's only one. It actually has the shortest length among all the paths in the equivalence class. So the picture that we know very well in the case of the free group of words, reduced words, actually makes just as much sense for paths of finite length. There is always a tree-reduced word in every equivalence class, and because of that it's pretty obvious that they form a group. Because it's obvious that if I take two paths of finite length in a vector space, I can concatenate them, and then I can tree-reduce what I've got. So that's a product, and it's another path of finite length, because the tree reduction only decreases the length. So it's closed under multiplication, and it has inverses because it's obvious that if I take a path and run it backwards, I get the inverse. They're obviously equivalent. So it's closed under multiplication, it has inverses, and with some more thought, you can actually see it's associative. That again is less obvious now because of the tree reduction. But it is actually a group. It's a fundamental group. It is the group of paths of finite length. Now, how on earth do you prove such a theorem? Well, to do so, you really need to go into the algebraic things, the equivalent of the Fourier series, if you like. And you also need to do some analysis on Rn, or indeed on your vector space. So the first thing you need to do, after all, we were talking about our path having finite length, so in some sense we've done it already, is put a norm on our space. Now the interesting thing is that even in Rn, it looks very much as if the easiest norms to work with is not the Euclidean norm, but the little L1 norm. And the reason for that is that we're going to look at lots of tensor products. And typically the tensor norm you want to take is the projective tensor norm, the biggest cross norm, the one with the smallest number of points in it. And little L1 spaces, you can compute the projective tensor product quite easily because it's just the little L1 of the product space. Whereas if you took a Hilbert space, the projective tensor norm is more like B of H, and it gets progressively more complicated as things go on. And so in practice, it just seems that it's an awful lot easier and a lot more explicit to work with little L1 than it is to work with the Hilbert space. The theorems generally tend to be true, all the rough path theory and iterated integral theorems tend to be true in any norm and appropriate tensor norms. But in practice, you seem to be able to do some very explicit analysis with the little L1 norm that you can't do with the others. But it's interesting, because if you're going to use L1 norm, have you ever thought what it means to be the length of a path? What is the length of a path in little L1? Well, one of the interesting things is, in general, geodesics are not unique anymore. If you take a path from here to here, that has the same length as that one and the same length as that one. So it's no longer a strictly convex norm. It's no longer got unique geodesics. So you have to be a little bit careful. But nonetheless, it seems a better thing to do. So we're going to introduce it for you, not because we have to, but because in some sense it makes it much easier to explain things, and because whatever you do, you're going to have to be concrete, and this is as good a choice of being concrete as any. So let's suppose we're in a finite dimensional space, and let's suppose that we have a canonical basis, which we'll call A1 up to AD, and we think of that as an alphabet with D letters. And we take the little L1 norm, which means that we just sum the moduli of the coefficients in front of the letters. That's what I mean by little L1. Now, associated with that space, I want to introduce the tensor algebra and the tensor series. So that sounds very frightening in general, but that's one of the reasons for doing it this way with you, is that it doesn't have to be frightening. If I have letters, I can form words. And I can take the space spanned by all the words, including the empty word. We have the empty word, we have the words with one letter in them, we have the words with two letters in them, we have the words with three letters in them, and we can easily make that a linear space by simply summing the moduli of the coefficients, which is actually the projective tensor norm on the nth tensor product, but never mind. We can easily make it a normed space, but more importantly, it's an algebra, because if I have a word of length n and I have a word of length m, just like the paths, I can concatenate them and produce a word of length m plus n. That tells us how to multiply basis elements, and of course the distributive law tells us how to multiply everything else. So this is really the space of polynomials in non-commuting coefficients with a norm on it. But it's also the tensor algebra, and if we allow ourselves infinite series of coefficients, infinite series of monomials, the tensor series if you like, then that is actually the thing that I tend to be interested in, and that will naturally emerge if you put a norm on. So this is one of our new objects. It's a Banach algebra of words, if you like.
So the tensor product of two vectors is what now?
It's defined by the distributive law. So a vector is a sum of basis vectors. Basis vectors are words.
So we go outside immediately, outside of the RD.
The original vector we have two vector spaces here. The first vector space is the vector space spanned by the letters, and the second vector space is the vector space spanned by the words.
Now
if you take the tensor product of the vector space spanned by the letters with itself, you get the space spanned by the words of length 2.
Okay.
Right? But if you take words and take their tensor product, you get words. So tensor product is simply a product operation on the space of words. But you're quite right, if you take the space of letters, or linear combinations of letters, the original vector space, then this is a subspace and the tensor product takes you immediately outside it. That's why it's called the tensor algebra over V. It's the simplest object that takes your vector space V, which has no multiplication, and embeds it into a space that does have multiplication. And it has the universal property that if you have a linear map from V into an algebra, then it extends uniquely to an algebra map of the tensor algebra into that algebra. And if you take the little L1 series, you'll see that that must always work by the triangle inequality. Okay, so that sounds horrible for a probabilist or even for an analyst. Maybe the little L1, the norm, is the only bit that seems at all comforting to one. But I'm now going to try and explain to you why it matters for paths. You see, we tolerated the fact that we could take our continuous function on the circle and replace it by a series of complex numbers, which seems a pretty unpleasant thing to do too, in some sense, right? I mean, a continuous function is something we understand, and this string of numbers is a Fourier series. It's just a string of numbers. You can do the same with your path. You can define an object, which I'll call the signature of this path, and it's defined on the whole path segment. And it maps it into one of these infinite series. It maps it into something we call the signature of the path. At the moment, I'm not going to tell you what the signature is, because I want to explain already why it's useful before we explain what it is. But it maps the path to a series, to a linear combination of words of arbitrary length. Now, the point that makes this map completely fundamental is that it's a homomorphism. We have an algebra on the right-hand side, as we've just had from the discussion, which was very helpful. But we also have a product on the left-hand side, This is without any of the theorems I was talking about. This is just the basic fact that if we've got our two paths in our vector space, we can always move the second one so that it's at the end of the first one and concatenate them. That's a natural product, and it turns out that it's a homomorphism. So concatenation turns to multiplication. It's also true that running backwards turns to inverse. So actually the range of this map is automatically a group, because this object is automatically a nice associative algebra. There's no messing with it. You know, you can just do the normal things with it. And so you have an associative algebra. You have inside it a collection of elements that's closed under multiplication, has inverses, so it's a group. So actually this signature is a map from paths with concatenation onto a group inside the tensor algebra. Which group is a difficult thing to describe, and it's just like the L1, which things turn up as L1 Fourier series is hard to describe. It's not easy to describe what you actually get here. The tail behavior is what makes it difficult. Locally on the first finitely many terms, it's easy to understand. It's the asymptotics that are tricky, just like the Fourier series. Of course, any first few terms can turn up. Okay, but now we see how to prove that there's an equivalence relation. Because if you can prove that two paths are tree-like, or tree-like equivalent, if and only if they have the same signature, well, this is obviously an equivalence relation. If you have a function and you look at the points that get mapped to the same point, this is an equivalence relation. A well-defined function, and you say A is equivalent to B if f of A equals f of B. That's an equivalence relation. So if you can prove this theorem, that the signatures agree if and only if the paths are tree-like equivalent, then you've proved it's an equivalence relation. You've proved all those things that we were talking about before, more or less. And Ben Hambley and I actually did prove this, and much, much more beside, in the paper I was referring to earlier. So that's one tiny little reason why you might look at the signature, because it helps you understand this basic property of paths of finite length. But mathematically, there are lots and lots of reasons why you'd look at this signature. But before we talk about that, we'll talk a little bit about just a mathematical definition of what it is. So if I have a path, gamma, then I can integrate it over the simplex u1 less than u2 less than un. So in effect, what I'm doing is I'm taking a random collection of IID times u1 up to un inside T. I'm sorting them. I'm looking at the direction of my path at the times u1 up to un. I'm tensoring them together to get a volume or whatever, and I'm taking the expected value. I'm taking the expectation of an empirical distribution of the directions of my path at the given orders. And actually that probabilistic intuition can be helpful. Now this is something I can do, and I can do with any path of finite length. I could do it for any rough path as well, but we're not going to talk about those today. Because a path of finite length is differentiable almost surely. And one thing you notice from elementary calculation is it doesn't matter at all your speed of parameterization. If you run the path faster, you run the path slower. If you run it fast in some bits and slow in others, it makes absolutely no difference. Because the faster you run it, the smaller, so the derivative will get bigger and it just balances out in the obvious way. Okay? So you may as well, and I think it's helpful to understand, imagine that you've always parameterized it at unit speed. That also is going to give you a nice understanding of how you parameterize the concatenations. Okay, but then it's a trivial exercise, and I want you to notice it, that we can actually control the size of the signature. If we have a path of length L, and we parameterize it at unit speed, then these things have all got modulus 1. sorry, modulus L. Well, doesn't matter much which way around. And it's an easy exercise then to see that it's actually controlled by L to the n, T to the n, and then 1 over m factorial. And where does the 1 over m factorial come from? It comes from the fact that this isn't an integral over a cube, it's an integral over a simplex, and there are n factorial simplexes inside the cube according to which way we sort the u's. So actually the nth term in the signature is decaying like t to the n, L to the n over m factorial. And in the one-dimensional case, this is just the nth term in the series for the exponential function. This is a sort of non-commutative path exponential of the path gamma. Okay, but we've got this obvious upper bound for its magnitude. And that will be important to us later on.
So the integral is a number.
The integral is a tensor.
So because I think the inequality suggests it's...
Well, there should be a norm sign. So I have simply forgotten to put norms there. Okay? I should, whoops. No, the integral is not a number. If it was a number, that would you waste a lot, because in fact you see you've got a geometric collection of numbers because the dimension of the n tensors is geometric, and I'm saying the whole lot put together has a norm. This is at most this. You don't want to do it term by term, it'd be quite wasteful. You're using very much that the norm of the product is less than or equal to the product of the norms. Sorry. Okay, so at least it's well defined. If you have a path of finite length or a rough path, you can certainly compute this signature. It's a theorem of Chen, and it's easy to do that it's a homomorphism, and I'm not going to go into that. What I want to talk about a little bit more is the fact that it gives a complete description of gamma up to this tree-like equivalence. And that's sort of interesting, actually, because we're not used to ways of describing paths that give us the path without the time scale. The Kolmogorov way of looking at a path or partially describing a path looks at gates at certain times and asks whether the path goes through the gates. This looks also at functions of the path, but global functions of the path, and interestingly, as I said, ignores the speed at which you go along them. So up to tree-like equivalence, it completely determines the path. So it determines the effect of the path on any differential system. That's sort of not completely obvious. It also, once you've reduced it and removed the tree-like pieces, it tells you things like the first exit position of the path from a domain, because that doesn't depend on the speed at which you run it. It gives you exit laws and so on. It has something else which probably should be interested in. The signature lives in the vector space. There's tensor algebra. So if we have a random path, you have a random signature. And if you take the expectation of that, which makes sense because it's in a vector space, at least if the law is compactly supported, this is like a moment problem, the expected signature determines the law of this measure on paths. That's not a very difficult thing to prove. It's to do with shuffle products and things, and I won't go into it. But it's like the Laplace transform. We all know that if we take the expected value of the function e to the lambda x, function of lambda, which is the random function that you get by selecting x, then this determines the law of x. Well, this is very similar. And it has the same sort of issues about moments. But it's actually quite interesting to reflect on the fact that it's the first real tool I think we've got for describing laws of measures on paths which does not hinge upon the Markovian structure or the martingale structure of the underlying process. This is really about ways of describing laws on paths. And for example, there's a paper of myself with Daniel Levin, where we actually explain how it's quite easy to calculate these expected signatures sometimes. And they form the basis of various numerical schemes. Also, you can do things like compute winding numbers. It seems an open problem at the moment to really use one's experts, use this knowledge we have in the signature to go back and extract basic information about the path, like how big an excursion it makes, its winding number around a point, all the things which we can prove are encoded in this signature. We're not that expert at getting them out. And that's, to some extent, what I want to talk about. You see, it is actually a very powerful tool because it gives you a graded summary of your path. It tells you step by step the most important features of this path as a control. The first term is simply the increment of the path. The word count if the path were a web page and the directions in the space were given by words. The second component gives you the area and so on and so forth, but as we now know, asymptotically they give the whole path, but they can be interpreted, at least for linear differential equations, as giving you a sequential approximation to the truth. So if we know the first few terms in the signature, we can write down asymptotic series to tell you the first few terms in the solution to the differential equation, to the approximation to the solution of the differential equation. We get better and better approximations. But actually, if it's a lattice path, you can go further. So for me, a lattice path, and indeed for the rest of this talk, is simply one that goes along an integer lattice. Right? So it's corresponding to words in A's and A inverses and B's and B inverses. Because then you can be even more precise. You don't need the whole signature to determine the path. If you know how long the path is, if you know that it has at most L steps, then actually you need essentially L terms in the signature in order to determine the path. The number of terms you need grows logarithmically with the dimension, or at least the proof grows logarithmically with the dimension. I don't know that anybody's proved that these are close to sharp. They're certainly not sharp, these estimates, but they're good enough to be interesting. But the fact of the matter is, if you have a lattice path, you don't even need the whole signature to recover it. If you know it's a lattice path, you already have enough information after a certain number of terms, which is linear in the length of the path. So, lattice paths are a bit special, but they're also special because they approximate paths of finite length rather well, but that would be a different lecture. So the fundamental question I wanted to talk about today, the one that's been stumping me for some time, is how do you go backwards? Suppose you find a path with a given signature. How do you find the... and you're given the signature, but you're not given the path. How do you find paths with that signature? How do you find paths that approximate to the original path because they have a signature up to a certain finite level the same, and they're not too long? If you've got your lattice path and you've given the signature of it, how do you find the lattice path back? Well, the last case is sort of easy in some sense. In fact, they're all easy in some mathematical sense, because we proved the maps one-to-one. And there's a theorem that says one-to-one maps have inverses from their range. So there you are, that's the answer. You know? And actually that's part of the problem, because it's true. Right? If you have a one-to-one function, it has an inverse, and that's it. So actually you need to be a little bit clear about what you're really trying to do. So what you're really trying to do, or what I was trying to do, was to find approximations that one could compute effectively to the real path. So if I take a sound, I compute the signature, I throw away the sound and just keep part of the signature, I would like to go back and produce a sound that sounds the same as the original one. I don't just want to be able to tell you, like a code, well, only the right sound is going to give this signature. So, I mean, I wanted to be able to invert the process and turn it from being a coding process into a recording process, where you could reproduce what had happened. So in the lattice path case, of course, you know, you can actually just enumerate all the cases. It's a finite set. But of course, the number of lattice paths grows exponentially and very rapidly. And so that's not the answer there anyway. And if you did that, it's certainly not going to give you a great insight into what to do in the continuous case. So that's the question I really wanted to address. How you go from the signature back to paths with that signature. And what I want to do is explain to you a series of ideas that have come together and which pull in some ideas from optimization, which at least provide an effective answer to this question under reasonable circumstances. And what I want to do is remind you of something called branch and bound. So we're used to the idea that when we approximate, if it's in low dimensions, we can normally do quite well with series. That's why Fourier series work. But we're also used to the idea that in high dimensions, series don't normally work. You do not use series to approximate measures, you use particles. And the point is that the particles you use vary according to the measure you're trying to approximate. The trouble with series is you tend to try and use the same series, whichever function you're looking at. Of course, it's not quite like that, because we understand that power series converge in patches, so if we're interested in the function over here, we use that power series and here that one. But we hope to use one series for a whole family of things. In high dimensions, it never works, which is why particle filters and things work much better. And branch and bound, in a sense, is exactly that sort of flavor. So the idea of branch and bound is typically that you have a tree. And on this tree, well, let's label the nodes in the tree by these underlined letters. And a tree has a partial order on it with the property that you're, depending on whether you think of them as children or parents, but your parents are totally ordered. You can always go back in a total order. And you have a function defined on each node. And you want to maximize it. So this is a nasty problem in general, because there are exponentially many points, and you'd like to find the maximum weight across all of them. Well, one thing you could do is some sort of simulated annealing. It's a large space, you can go back and forwards, you can try and find it. But actually, I think it's fair to say that what I'm going to tell you today, which isn't to do with me, I've realized that it's quite a big literature on it, probably supersedes simulated annealing in any situation where it can be applied. So the idea is that if you've got a little bit of extra data, and I'm going to call this extra data a bound, you can actually do quite intelligent things, and the efficiency of the algorithm will depend dramatically on H and B, but I want to explain it abstractly for you before one starts to try and think about particular choices for B. So the idea is that first of all you have this objective function H that you're trying to maximize, and then you have a bound function, and the idea of the bound function is the bound is a guarantee that no child of my node, if I go further down the tree than where I am, has a value for the objective function that's bigger than the bound. So the bound is a global bound on how well you're going to do if you proceed down below me. And the point is that at each stage, as soon as you have that, you have an algorithm. The idea is that you have, at any given stage, explored a subtree of this tree. And so you have an estimate for the max, which is the max you've seen so far. And now you look at all the children, the direct children of the tree you've got. For each of them, you have an upper bound for how well you can do if you develop that child. You realize that that child is never going to achieve the level of the maximum so far, so you kill it there and then. And you only leave the children who have potential, not necessarily realizable, but at the moment who have potential to exceed the maximum you've achieved so far. And those children you then explore again, and you kill off those who have no hope. If you think about it, that's actually how we do manage intellectual property and ideas. You know, we have ideas that seem to be working, we explore lots of ideas, then we figure out that those ways aren't leading us anywhere, so we forget them and we keep close to a single trajectory or a few trajectories that seem promising. And mathematically, it's fine, and the quality of it in reality depends critically on H and B. But one place where you'll find it in the literature is actually in optimizing Lipschitz functions on cubes. And so a cube has a natural tree-like structure. We can divide it, or a rectangle. We can divide a rectangle along its longest edge and split it into two, and so we see a natural tree coming out of a cube in any dimension. And let's suppose we had a Lipschitz function on that cube and we were trying to maximize it, or at least find points near the maximum and estimate the maximum. Well, you can just take as your objective function the value as the center of each of these squares, or rectangles. And the bound, we simply use the Lipschitz norm to say that it can't be bigger than its value at the middle plus the distance to the boundary of the region. Just use the Lipschitz norm. And then if it's small in some square, you know that it's at the center it's going to be smaller than the whole square, so it can't exceed the value somewhere else you've already experienced. So this is a natural pair of functions, an objective function and a bounding function coming from the Lipschitz structure on H. Looks very abstract, but sphere packing is an exact example of this. So sphere packing, you have n spheres in d dimensions in a cube, say. So that actually is a point in the nd dimensional cube. And what is the function you're trying to maximize? You're trying to maximize the minimum distance between the points, and that's an obvious Lipschitz function, because it's the min of the distance to each point in turn, and the distance to a point is Lipschitz with norm 1, and the min of Lipschitz functions is Lipschitz, so it's obviously a Lipschitz function with norm at most 1. So you see, actually, although it looks like an abstract problem, sphere packing, which is an NP hard problem, you might remember, already fits neatly into this framework. And in fact, I came to it completely reverse. I realized it was an example and so on, and then I Googled sphere packing and Lipschitz and branch and bound, and you find loads and loads of papers, and it's an obvious way to do it. But anyway, so the idea is an important one, I think, and it doesn't belong just in the optimization world. It is a way of reconstructing values, the maximum of a function, from the function in an empirical, in an effective way. So what I'm going to explain is that at least in the lattice path case, you can really do this for the signatures. So in the end, if I've got time, I'll show you a little bit of program, and I did actually write abstract branch and bound code, more or less like I've been describing, and then I found the right H and the right B for the signature to make it all work for this example as well. And if I have time, I'll actually run it to show you that you can do it on sensible examples. So we already have this upper bound on the signature. Another way to look at it is if I give you the signature, I have a lower bound on the length. Rather than think of it as an upper bound on the signature, think of it as a lower bound on the length. So given a signature, I have a lower bound for how long the path can be. Now actually, again, if you look at the paper of Ben and myself, we actually prove that you can recover the length from the asymptotic behavior, sort of Tauberian theorem, under conditions of continuity of the derivative of the path, and the lattice path doesn't quite satisfy them, but it satisfies well enough that you could make the same proof work. So you actually have sort of asymptotic lower bounds on the signature too, that the signature will decay like L to the minus n times 1 over n factorial as n goes to infinity. So in some sense, this inequality is really quite sharp. It's not just a sort of random remark. So how can we put that together? So we're going to proceed by induction. Lattice paths, thank God, are finite and so on. And the idea is quite simple. We start with the signature of the lattice path gamma, and we don't know gamma. We only know the signature of gamma. And now we consider potential factorizations. So we take an initial, we look at the collections, if you like, of a path Tor, which might or might not be an initial factorization of our path. The path run backwards and then gamma. So all of these are the same as gamma. They all have the same signature. As a result, we can sort of record the pair, the path segment and the signature of this bit. And the signature of this bit by the homomorphism is just given by the inverse of the signature of the path we know, Tor, and the signature of the path we don't know, but we know the signature, S of gamma. So for any initial segment, which may or may not be a real initial segment of gamma, we can look at the pair, Tor, and then the signature of Tor run backwards gamma. Now, the point is, if we really run along the path, the path gets shorter. If we go in any other direction, the path gets longer. We can look at the signature, and if it gives a lower bound for the length, which is bigger than the original, than the length we know, with Tor taken away, we can reject it. If we've got this, the signature gives us a lower bound on the length. If we can prove that we've made the length of the path longer than it should be, it's clearly not a legitimate Tor. And that's actually the bound in the argument. The length that you're trying to minimize is actually the signature. You're trying to make it go to 0. You're trying to actually minimize the length in this case. So what you do is you look at all pairs, admissible pairs, if you like, of an initial segment and the signature of what will be left. But you only accept the ones where the signature of what's left does not imply a length that's longer than L minus K. And you start with a trivial case. You can start with C0 because you have the empty path and the original signature, and that's going to work. And now you move out in what, now you see the tree, you move out by adding one letter, an A or an A inverse or a B or a B inverse, to the path. And so now you get Tors of length 1, you get C1, and you reject the ones that can't possibly produce the answer. And you just keep going. And what happens, amazingly, is that because everything is so sharp, it's really quite efficient. It is absolutely amazing, as in concrete examples, just how sharp it is. Now, I don't have a theorem yet that quantifies how sharp it is, but originally I just wanted to be able to do it, and that I can certainly do. It seems that the upper bound is sufficiently sharp that you get almost no wastage. As soon as your path starts to go wrong, the length starts to increase, and not only the length starts to increase, the witness to the length in terms of the first few terms in the signature gives this length away, and you're able to reject it. So in this way, you grow your path down the real path, and it really works. And you stop when you actually get the path that works. And so, for example, you can take a random path with 23 steps and recover the reduced path and signature. And I'm actually going to try and show you that. Now, just to give you some idea of what these things do in real time. So this is on my laptop, which is not a particularly fancy laptop. It's 2 years old or 3 years old. And in fact, I'm going to... I should have written a proper little example for you, but I didn't have time. So I'm going to work out the first 15 terms in the signature. There are 2 letters. And interestingly, I have to work over arbitrary precision in rational arithmetic, because otherwise the errors in the signature, the bleeding, means you work out far more terms than you really need to. And I'm going to do a random path. I think with 25 steps in it, but let's just see if I can find out what, 27 steps in it. Okay, right, so there we are, and that's how I'm going to finish. So, to give you some idea of what it does in real time, I hope, yeah. So, it's now computing the signature of this 27-step path to level 15. So now's the path, that's the path, just the steps in the path, and now it's trying hard to go from the signature back to the path, and it'll take quite a time. And it'll give the path backwards, but it'll give the reduced path. So it'll be shorter than this one, because this is a random path, and so you'll get A and A inverses, but the reduced path will be given, and it actually gives you backwards. There we are. So there we are, that does it. And so still, this is quite a long path. I mean, it's not nothing, a 25-step random path. So going back. So if I've got a minute left, I'll just show you something else, because I haven't talked too much about the signature. There's a lot of structure in the signature. And I've been talking about the actual signature. Well, the signature, if you didn't notice, began with a 1. The empty iterated integral. You can't see it here, and I don't want you to particularly see it here. I mean, basically, this program, I can draw a path, and it will compute the signature of the path. But the thing I wanted to get across is there's a huge number of terms, and but they're not all needed, because it's not at all a generic element of tensor algebra. It's a very special group. And if you want to understand it, you really ought to look not at the signature, which is important for what we were doing just in, but if you want to understand it in a compact way, you want to look at the log signature, and you'll see immediately that the amount of data needed to capture the same path gets a lot smaller. There's two ways of looking at it. The log is great for compactness, conciseness, and understanding it in certain ways, but sometimes you absolutely have to transform it into the whole signature like we were just then, if you want to use it in other ways. The inversion idea absolutely used the signature and not the log signature. That's really all I wanted to say. Thank you very much indeed, and I hope you found it interesting.
Thank you. Are there any questions?
So you mentioned the your asymptotic theorem on the norm of the signature being equivalent to I forget what the formula was, L to the power n over n factorial.
Yeah.
So
the accuracy of that depends a little bit on what you know about the smoothness of the path.
Okay. And my question was whether the pictures that you've shown us here depend on having a sufficiently long path, taking what? Taking n large enough. Is it going to be a problem if you're trying to encode your path with a small number of terms of your signature?
Absolutely.
Yeah.
Absolutely. I mean, to get more information about your path, you need more terms in the Fourier series, so to speak.
Yeah, right.
I mean, and there's a trade-off between the two, and of course, computationally it becomes a nightmare. But that's true, you see. I mean, a complex signal is a complex object and contains an enormous amount of information. If you can break it up into little pieces, it's something.
Yeah. During your talk, you mentioned dynamical systems, differential equations. Can we get some insight into, say, differential equations?
Lots.
From the concept you developed.
Lots.
For
I mean, no, the whole Magnus thing, I mean, no, it's very closely connected to many things like that. I mean, both deterministic differential equations like area equations and stochastic differential equations as well. You get lots of insight, but it's a different lecture. There's a limit to what I can talk about in one lecture.
So we should.
So it's deliberately amputated. I mean, yeah, for sure. It's in fact a very, very natural object for doing numerics of controlled differential equations.
I'm a little bit puzzled that you don't need the whole information of your signature in order to recover the path in this equivalence relation, because maybe then the equivalence relation is too crude. Or, I mean, if you think now, if you believe in signature, yeah, then you would maybe conclude that maybe the equivalence relation is good for reconstructing the part, but nevertheless it's somehow too crude because you lose information because you have much more in the tail.
So hang on, which say it again? You talk about the difference between the signature and log signature.
No. I'm talking about your theorem that if two signature, I mean, you said that you don't need the whole signature. You only need it up to a certain end, depending on the.
That's if it's a lattice path of length of most depth.
It's only for the lattice.
Absolutely.
Okay.
If it's a path of finite length, you would certainly need it all.
Okay, and I understand.
Right? It's once you constrain it to be a lattice path,
Right.
then you actually only need a bounded number of terms, and you have a theorem that that's enough to give it all,
I missed that point. Okay.
right? And it's quantitative. No, you absolutely need the whole series.
Yes.
Andy?
Can you quantify the complexity of what you're doing as an?
Probably can, and it's probably painful. But you've got to be very careful now, because I think we're exactly in the world, which I think is modern computer science, where people have realized that there are lots of NP hard problems, which most of the time you can solve quite easily. So the goal is to find algorithms which work well when you can do well, and which cost you a fortune when you have to pay a fortune, yeah? And there's no simple answer to that. So what I seem to be doing here, for sure these are exponential problems.
Yeah, but you might get an epsilon approximation in an algebraically growing time.
I don't know, but I might. I haven't done that. That's exactly what I should be doing.
Kind of rephrase my understanding of Andrew's question. I mean, the exact same question, if you look at approximation theory, right? I mean, in the sense of function approximation theory, a la, wavelet. I mean, this is exactly like a pruning algorithm for a wavelet reconstruction or a Bezoff space reconstruction. And the you can exactly characterize the space by the approximation rate, right? As you kind of prune the subtrees, right? That's kind of what you're asking, right? So
Yeah, I agree. I mean,
this is very much like what you do in
but up to now, I've been having difficulty. I'm sure some of these things are genuinely exponential, right? They have to be. There's no free lunch here, right? But I'd like something that didn't take more exponential computation. It has to. At the moment, I'm just happy that I've got this far. But now, having got this far, I completely agree that one should analyze the actual effort really required to do it, because otherwise you can't compare and move on, actually. I fully agree with that.
Other questions or comments? If not, we can try again.